It's basically a work that combines two things that shouldn't be in the same sentence: spatial branching and convex MIQCP. And I'll try to explain why this actually makes sense with two examples. The first one takes the first 4 points of the schedule, and the last one is a more recent work that will only take a couple of minutes to explain. This problem you're probably familiar with, all of you. You have a bunch of points in RD, and some of them, so unfortunately the literature calls the data x and y. So x of I is the ith point, which is in a d-dimensional point. Every point I has a label associated to it, which is -1 or 1. And we want to separate them with a separating hyperplane. We would like to find the hyperplane. So our variables, the decision variables, are actually the w and b. We would like to separate those points so that all the points with label -1 are on one side, and all the points with label +1 are on the other side. So in principle, we could write the two constraints for different values of the label, or we could condense them into a single constraint, which is basically just the label multiplied by the slack of the x point with respect to the variables w and b is greater or equal than 1 for every point. Clearly, this would give you an infeasible problem, especially for sets of points with noise or sets of points that simply can't be separated by hyperplane. So in general, instead, if there are points that fall on the wrong side, we give a penalty. So we express a penalty that is only growing for the violation being from 0 to 2, and then stays flat after 2. So this is a ramp penalization term that we add for every point that is incorrectly classified, so to speak. And here you can see that basically the violation itself is a segment that goes from just on the other side of the line until the point that has fallen on the wrong side. And the objective function, so the penalty term that we add to each violation, is in fact not the whole segment, but just the portion of the segment that is between 1 and -1 of the supporting hyperplane. So this becomes an optimization problem where you want to minimize the total penalty. You want to be able to classify as many points as possible, so you just basically try to minimize the total penalty, where the penalty is this ramp loss that I just said. You would be tempted to use a solution WB where W and B are very large, because that would basically make this term -1 and 1 a little bit less impactful. But that will give you a lot of numerical problems. So in general, what's usually done is give an objective function where the total penalization is counted, and it's a lot more important. But you also want some stabilization term, which in this case is just the norm, the squared norm of the coefficients of the hyperplane. This is basically the paper where a few works have started from. And what this gives you is a mixed integer quadratic optimization model where the only nonlinear part is just that square norm. So very nice, very smooth, not even very significant in terms of the value of the objective function term at the objective function. The rest is only linear constraints and a few binary variables. I have to change the notation because that will make the following a bit more comprehensible. So instead of having a vector w and a scalar b separate, let me just condense all of it into a single vector g. So g now is my main continuous variable, the data that's specific, so the variable that gives me the full separating hyperplane, and all the data, so the x and the y that was given as an input, let me condense them into a single vector vi, one for every point I from 1 to n. So what happens now is that the weighted violation that was on the left-hand side of this big M constraint becomes just a simple scalar product G transpose VI. So from now on, we work on this MIQP, where G is continuous, psi is the ramp term that goes from 0 to 2, and Z is the only integer, and it's binary, it's the only discrete variable. There's one such variable Z and one such variable psi for every point that I'm trying to classify. The G instead is a vector of dimension d plus 1, where d is again the dimension of the points I'm trying to classify. The crucial bit, since it's also the only constraint I have pretty much, is that this big M constraint here has a big M, that's a multiplier of Z, whose value depends very much on the bounds on G. So in other words, I have to make sure that this inequality can be violated by adding an opportune value of Mi times Zi if Zi is equal to 1. Because Zi equals 1 means the point is misclassified. I want to add a penalization term for it. Let me point out, because this is the crucial bit of the whole presentation, that M of I depends strongly on the bounds on G, because V is given, it's input. And you don't need to be a MIP expert to notice that the coefficient matrix has a very peculiar structure. It's very dense in the columns corresponding to G, because those are all my points. They can also be sparse, but in general, I can anticipate that they can be dense. The remainder of the coefficient matrix is in fact sparse. It's two diagonal blocks, both for the Xi variable and for the Z variable. Well, the Z variable is just a diagonal block of big M's, which means that basically if I have a lot of points, so if n is much larger than the dimension, then given that I'm trying to solve it as an MIQP, so I'm going to solve it with a MIP solver like Grobi, Express, whatever, I'm going to have to branch on Z, on every Zi variable. Well, not every Z variable, because obviously that would take a while. But every MIP solver will basically just take Z as the branching variable and nothing else. But branching on Z variables has only an effect on that single comparison, violated versus non-violated, or classified versus misclassified point. So the basic idea here is probably a blasphemy in the MIP circles, but it's to branch on continuous variables. So given that I have very few G variables, there are only d plus 1. What I suggest is to branch on G variable and see what effect it has on the problem. Now, branching on G variables means that now you have to rework your branching framework. Every time you have a node that doesn't obtain a feasible integer solution, you have to decide what variable to branch on. So what of the G variables with index between 1 and d plus 1. And especially because G variables are continuous, what branching point? Which obviously is not a problem if you have a MIP, because in MIP you usually just have to branch on rounded up and rounded down value of a given variable. So spatial branching consists of finding an index j and a branching point tau so that I get what I want. And what I want is really to make sure that the two nodes that I obtain from branching have as much of a gain in objective function value as possible. Or better, the minimum gain in objective function value that I get between the two new branch and bound nodes is maximized, because then I know that the lower bound is going to grow. So in principle, I could try to look at it from a slightly more MIP-ish point of view by rewriting the main big M constraint as a constraint on the Xi and the Z variable. In other words, I want that mixed integer left-hand side to be greater than or equal to, well, a violation. The violation is precisely 1 minus G transpose times V. And M itself, the big M on every constraint for every point I, is calculated simply on the right-hand side. All I need to do is that Mi be exactly the same as the right-hand side. Now the right-hand side has an upper bound that's given by 1 minus the lower bound on the product G transpose times V of I, which is also defined by simply taking the data itself, the VI vector, and the lower and upper bounds on the G. So I can condense it, I can write it simply by taking a D coefficient that multiplies the data V, and D is simply a function of the lower bounds on the upper bounds of variables G. So as usual, not in mixed integer linear programming, but definitely in mixed integer nonlinear, non-convex programming, lower bounds and upper bounds on continuous variables are more than important. So let's delve a little bit more into this big M business. So basically, M of I, as I said before, is simply the big M constant is equal to 1 minus that scalar product between the data I have and the function of the lower bounds and the upper bounds on G. And I only need to take the big M's that are actually non-negative, because if a big M turns out to be negative, obviously that the constraint doesn't need to be imposed even. So in principle, what I could do is the following. Okay, so why all this discussion on the big M constants? That's simply because the big M constants depend on the bounds on G. If I change the bounds on G by branching, obviously there's going to be some knock-on effect on the big M constraints themselves. And I would like to know what happens to the two branch and bound nodes that I'm going to create when I decide what is the new lower bound on one side and upper bound on the other side on variable Gj. So for the left branch, where I simply impose Gj less or equal than tau, I didn't decide J yet or tau. So I need to find out how to best compute them. The new upper bound is obviously different, because now the big M needs to be, again, an upper bound on this guy over here. So given that the upper bound of one of the G's has changed, so will this big M constant. And the same is going to happen for the right branch, where Gj now has a new lower bound. So the lower bound changes makes the big M change depending on whether the data is the data Vij is positive or negative. So in principle, I could do the following. Okay, so for the left branch and the right branch, I could do the classical strong branching approach, where I take the decision that I want to simulate, solve one LP, or QP in this case, see what the lower bound gives me. So I don't solve it to full integer optimality, because that would cost a lot. But I can still solve a quadratic problem with the C, Z, and G variables, and I just relax integrality on Z, simply because in that way I have a nice convex quadratic problem, and it gives me an estimate for the new value of the objective function once I add this new lower bound to the variable Gj. And I can do the same for the right branching node, so I compute another function that is basically a lower bound on the MIQP I would get on the right branch once I impose the right branch constraint. Typically, but that's not necessarily true for every solver, what you could think of is you get a score for every decision defined by a variable Gj and tau that is given by the minimum of those two gains in objective functions, simply because I want to make sure that whatever decision I make on both sides, on both subtrees I'm going to generate, I get a decent gain in objective function. And then, once I tried a lot of J's and a lot of taus for each J, I can select the J and the tau that give me the best possible gain in score. All I have to do is then, for example, sample M values of the value tau for every possible, for each of the D+1 G variables, solve for each of them two convex quadratic optimization problems, and then finally I get possibly an estimate of the score, an estimate of the improvement in the objective function after I don't know how much time I spent in solving these QPs. Clearly this is unreasonable. I would spend even more time in strong branching, and as we learned from Prachi just a few minutes ago, solving an LP is not exactly the solving a lot of LPs at every node is not exactly the best thing to do, which is the reason why strong branching is usually done in a limited subset of nodes in every branch and bound process. So at this point I was ready to give up. Not really, because if you think about this, one heuristic way to solve these two guys is to pretend for 1 second the G is fixed. So instead of solving a lot of convex quadratic problems, we rather fix G, and what we get is a completely different new problem, because now that G is fixed, the problem is completely decomposable. And for example, the left branching problem, the right branching problem is pretty much the same, becomes, well, first of all, the one constant is no longer quadratic because now the quadratic term is constant. And most importantly, this problem on only the xi and the z variables becomes decomposable. Because as you remember from before, their coefficient matrix is is diagonal, so you can solve, instead of solving a single, rather simple LP, you solve n LPs of very, very, very simple structure. Again, this is a MIP workshop, so I don't need to tell you how to find the optimal solution to this problem, where I have a single xi variable and a single z variable, and those in red are the only feasible points. Clearly, there is a closed form solution to this problem, which I can find in a couple of computations. But now I can go back and say, so this is a surrogate version. This is a very approximate version of those convex quadratic problems that was unreasonable to solve in my strong branching approach. And now I can actually do what I said before. So even if I sample m values of tau between lower and upper bounds on the variable gj, I can reasonably find a good branching point with n times d estimation. So the complexity for finding heuristically finding a decent branching rule is relatively simple. So I implemented in C, and I tried both Express and Cplex, which have a nice branching callback. I didn't implement it in Python for reasons that will be clear in the second part. There was a set of instances that we used in one paper that we wrote some time ago, and that actually used a branch and bound with extra cuts and also with some optimality-based bound reduction approach. And those 35 instances, for some reason, were now the benchmark I wanted to use for this approach. So the simple comparison I ran is this state-of-the-art from this paper, where there are some bound reduction, there's some optimality-based bound reduction, and something else, and some extra cuts that simulate the behavior of a global solver within Cplex. And then I gave a 2-hour limit. The results are here. So this is a classic approach, and this is approach with, well, it's basically a strong spatial branching, right? And I could easily tell, look at my branch and bound time and how it's better than the classical branch and bound time. I don't want to say there's like an order of magnitude improvement, because that is not really the point. I would prefer to drag your attention to the ratio between the branch and bound nodes of the classical approach and the number of branch and bound nodes of this strong branching approach. So the first instance is ridiculous. We go from 13 million nodes to 6,000 nodes. So that's 3 orders of magnitude. The ridiculous part here is that 13 million nodes is a lot of branch and bound nodes. So these instances are 2-dimensional. So D is 2, G is a 3-dimensional vector. The lower and upper bounds are usually between The lower and upper bounds are usually minus 200 and plus 200. So if you had a hypercube with lower bounds minus 200 and upper bound plus 300, you could easily partition grid that hypercube in three-dimensional hypercube into small hypercubes and easily reach 13 million small cubes, where basically the G vector is constant. And you can easily compute the violation, the total violation, the objective function for each such member of the grid, and find a feasible solution, find an optimal solution much faster than Cplex or Express do in 13 million nodes. For completion, I just separated the total time here from the single branch and bound time. The total time is the one that comprises the extra bits, the extra bound reduction done in the classical approach that is also performed in the spatial branching approach here. So that the branch and bound time to compare is actually these two columns. This is another set of instances from the same paper. There are classes. So there's a class 3 where basically we repeat the same results. So the 2-hour time limit is reached by the previous approach, and the new time is 6 seconds, not more than 12 seconds. All of them. In some other classes instead, and I can tell you later if there's time why I think that's the reason. It is actually the classical approach that works best, although not by a lot. Probably the worst is here, where classic approach is 1 second and the spatial branching is 178 seconds, only in branch and bound time. Any questions so far? So I mentioned both this paper from which the instances have originated, this other paper where we elaborated on how to solve it efficiently, and the top paper is an extended version of this talk that it is an optimization letter. There's a couple of other interesting articles in the area, especially this, because it gives me inspiration for another idea. If you can do strong branching on the G's, then you can also do something feature selection, in the sense that if you can restrict the values, the lower bounds and the upper bound on the G, that means that if you're looking for a hyperplane whose components G all have limited support, that means that you can, by some strong branching, by some branching rules, you can easily set to 0 some of the other components of G. Do I have time? Yeah, been fast. Application number 2, again, will more or less repeat what we've done so far, in the sense that now we have a set of endpoints also in RD, in D dimensions, and we have a given number k, and we would like to partition all these points in k clusters so that the total distance from each point to the centroid of the cluster, the total such distance, is minimized. So the problem consists in finding the centroids. So that's the only information I really need. That's the decision I need to make. Find the centroids x1 through xk, all of them are in D dimensions, of course, that minimize this objective function. And it's not a coincidence that the objective function and the whole problem itself, which is based on that single variable, that single class of variable x. However, this is clearly a non-convex objective function. Modeling this can be done using second-order cone. And in fact, there is a mixed integers SOCP model that was described by Nelson Maculan and co-authors. And I will briefly, but not so briefly, go over it, because clearly now the function has changed a bit. So we want to minimize this function, and P can be either 1 or 2, so I'm either minimizing a linear function or a quadratic function, and Z is simply the distance of every point to the associated cluster centroid if it is associated to that cluster centroid. And the decision whether you assign point I to centroid to cluster J is in the binary variable Yij. So you need another, once again, big M constraint where Yij determines whether point I is assigned to the cluster J. And if that is the case, then you want to make sure that the component Mijl for dimension L for cluster J and for point I is at least greater than or equal to the one-dimensional distance between the centroid coordinate and the point's coordinate. And you just collect everything into a second-order cone that's right here, and Zij is precisely the Euclidean distance between point I and centroid J if point I was assigned to centroid J. And the objective function is either is either quadratic or linear, depending on whether you have these two so-called unitary weighted Weber problem or minimum sum of squares clustering problem. One known method for the first problem, the unitary weighted Weber problem, is k-means. This is what k-means was written for. Now, the absolute value there can also be linearized, so you end up with two constraints for each dimension, for each cluster, and for each point, and those are two constraints over there with different big M's. So I define just an M prime and an M double prime depending on what part of the constraint I'm enforcing. And once again, given the lower and upper bound on the cluster centroid coordinate xjl, I can get different values of big M's. So clearly, if I do, if instead of relying only on the variables, on the binary variables Yij, which are the only binary variables here, so this is what any MIP solver would do, I would like to branch on the xjl variables. One reason that is similar to the reason why I chose spatial branching for the previous problem is that if you have a lot of points, then you have as many Yij variables as you have number of points times clusters, times k, the number of clusters. While here, instead, the variables xjl are in number, equal to number of clusters times number of dimensions. So once again, you have possibly far fewer xjl variables than you have Yij. So this is a very recent project which I started with a master student, and the idea is simply that if there is an xjl such that the lower bound and the upper bounds are far enough, then we split, we branch on xjl right in the middle point. So it's a very, very simple branching rule. So not really a very efficient one. I don't do any strong branching here. I simply branch in the middle of xjl, and we always take the xjl for which the gap between lower bound and upper bound is maximum. Once we do that, we get new values of the lower bounds on one side and the upper bound on the other side for xjl, which means we get new values of M prime and M double prime. If we do this, then we add to the model at every branch and bound node the tightened versions of these big M constraints, and we proceed. So also a very simple idea. We used instances that we found on the literature. The Ruspini instance is probably a proper instance of a clustering problem. Iris and WDBC instead have values that don't really, are not very suitable for Euclidean distances because they simply have different units. So we tried Express and we used the Python interface for Express, and we gave 1 hour for all the tests. So in this table here, and then I'm done. I can show you what happens both to the time and the lower bound I get when using this spatial branching and when not using the spatial branching. So in between parentheses is the gap if we reach the 1 hour time limit. Otherwise, that's the time we take. So for this, probably the more representative, the easiest instance, that is Ruspini, for values of the number of clusters equal to 3 and 4, we can actually solve the problem to optimality. And with the classical method, we can't find an optimal solution in the 1 hour time limit. For the other instances, those are a bit harder because they contain a larger number of points. But still here, for instance, we managed to solve it in 28 seconds, and the classical, sorry, no, never mind. So this is a lower bound that we get after 1 hour, and this is a lower bound we find after an hour without the spatial branching. And as you can imagine, because of the structure of the problem, every MIP solver begins with a lower bound that is equal to 0 for a long time for quite a few branch and bound nodes. I'm done pretty much. I would like to finish with one consideration. The results here are decent for this second approach, even if in principle, what happens with strong branching is with spatial branching is the following. The approach without spatial branching doesn't use any callback. So it's express run on the instance as is. The approach with spatial branching using callbacks is using callbacks. The wrong thing about using callbacks in Python is that Python is single-threaded. Yeah, if you have a parallel branch and bound, basically every time a callback is called, the execution is basically slowed down to a single threaded, especially if other branch and bound somewhere else in your computer need to call the callback. Without even mentioning the fact that these callbacks were implemented very plainly, which means that they might have been made a lot more efficient. Even so, I think that there's the approach seems promising, especially for I mean, it's clear to see from the first instances. For larger instances, we probably would need a C implementation as happened for the other problem. Thank you.